Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to discuss the matrix inverse. So in this topic, we will find an algorithm for calculating the inverse of a matrix. We will look at some examples, and then we will consider the numerical stability of finding the inverse of a matrix. In secondary school, you learned that a function that mapped the reals onto the reals, for such a function to be invertible, it had to be both one-to-one and onto. For example, if it was not one-to-one, then there would be at least one y value such that there were at least two x values that equaled that particular y value. Well, if that's the case, is the inverse of y equal to x1 or is it equal to x2? The inverse is not unique. So therefore the inverse is not a function. If the function was not onto, there would be some y values such that there was no x value such that y is equal to f of x. And therefore, for some values, it's not even defined. All right. So thus, a function had to be one-to-one and onto. You could find the inverse of, for example, x cubed, which is the cubed root of x. Now, let us start with a linear operator mapping Rn to Rn. That's A is in the collection of all linear operators on Rn. That matrix is invertible if there exists a matrix A inverse such that A inverse times that matrix A is equal to A times that inverse, and those both must equal the identity matrix. So for a matrix to be invertible, it must be one-to-one and onto, same as with real valued functions. Now, if it was not one-to-one, then the dimension of the null space would be greater than 0, and thus the pre-image of the 0 vector is not unique. So the inverse is not a mapping. If the matrix was not onto, then there would be vectors u such that that vector u has no pre-image in R to the n. Consequently, A inverse of u would not be defined. Consequently, a matrix is invertible if and only if the rank of the matrix is equal to n. For if the rank of the matrix is n, then it is both one-to-one and onto, and thus it is invertible. If the rank of the matrix A is n, then there must be a sequence of row operations that transforms that matrix into one that is upper triangular, and that upper triangular matrix must also have rank n. Now, each row operation can be written as a matrix. So consequently, if there were n sub 1 row operations that transform the matrix into one that is upper triangular, here represented by a capital U, then that is the same as multiplying A on the left by that sequence of row operations. Now, if the rank of A is equal to n, then the diagonal entries of the matrix U must all be non-zero. So they are all invertible elements of their own field, be it the reals or the complex numbers. Consequently, we can find another n operations that transforms the upper triangular matrix into one that is upper triangular with all the diagonal entries being 1. So essentially we multiply the first row by the inverse of the diagonal entry on the first row. We then multiply by the row operation, which multiplies the second row by the inverse of the second entry on the diagonal, and so on and so forth for each and every entry on the diagonal. Now, suppose we have a matrix like this. It is a matrix where all of the entries on the diagonal are now 1, and the only non-zero entries are above the diagonal. Could we not apply further row operations to eliminate all the remaining non-zero entries above the diagonal? Well, actually, we can. What we can now do is start with the last row and add an appropriate multiple of the last row onto the second last row to eliminate the one non-diagonal entry in the second last row, and then repeat this operation. So we can actually find a sequence of n times n minus 1 over 2 row operations that transforms the matrix on the left into the identity matrix. We would actually start specifically with this particular row operation where we are adding negative u prime sub n minus 1 n times row n onto row n minus 1. That's going to zero out the entry above that last diagonal entry. Then we'll proceed up the matrix to eliminate further entries. Okay. Thus, we started off with a sequence of row operations that got us to an upper triangular matrix with 1s on the diagonal. And again, if applying additional row operations is nothing more than multiplying on the left by the appropriate row operation matrix, then there are an additional number of row operations that now convert the upper triangular matrix with 1s on the diagonal, that convert that to the identity matrix. All right. So notice, therefore, in this case, we can group all of those row operations together, and if we multiply them all together, we get a square matrix. And that square matrix multiplied by A gives us the identity matrix. Therefore, the product of all of those row operations must be the inverse of the matrix A. Now, the last thing you want to do, however, is to calculate all these row operations and then multiply these matrices out. Probably suboptimal. However, we do have to have some way of finding the accumulated effect of all those row operations. So here's our strategy. We will start with the matrix augmented not by a vector, but now by the identity matrix. Now, here's an example of one such matrix augmented by the identity matrix. Now recall that applying a row operation onto a matrix is the same as multiplying that matrix on the left by the corresponding row operation matrix. Okay, but recall, however, that multiplying on the left by a matrix is the same as multiplying each column of the matrix by that matrix R1. All right, so now R1 times that augmented matrix is simply the matrix on the right. Now, notice, however, that this is actually the matrix R1 multiplied by the original matrix on the left of the augmentation, and on the right we have R1 times the identity matrix. Oh, but R1 times the identity matrix is R1. So what we have now is the row operation R1 applied to this 2 by 4 matrix is the matrix that has on the left R1 times the original matrix, and on the right the row operation matrix itself. With a little thought, you will see that if we applied 2 row operations on this matrix, then that would have the same effect of applying those 2 row operations onto the original square matrix on the left of the augmentation, and on the right of the augmentation we would simply have the product of those 2 row operation matrices. Thus, if we now apply all the necessary row operations to convert the matrix on the left of the augmentation into the identity matrix I, then the right-hand matrix is actually going to store the product of all the corresponding row operations. That is, the right-hand side is going to be the inverse of the matrix. So, for example, if we wanted to find the inverse of the matrix 2, -0.8, 1, -4.4, we would set up the augmented matrix as follows. We would now apply row operations to convert the matrix on the left to upper triangular or row echelon form. So we will add -0.5 times row 1 onto row 2. Notice that the matrix on the right is that matrix that represents the row operation of adding -0.5 times row 1 onto row 2. Now, if you'll notice on the left, the matrix is now in row echelon form, and it is a diagonal matrix with non-zero entries on the diagonal, and therefore it is invertible. If any of the entries on the diagonal at this point were 0, then the matrix would not be invertible. However, now we will carry on. We will multiply row 1 by 0.5. Now, the matrix on the right is now the product of the matrix that multiplies row 1 by 0.5 times the matrix that represents the row operation of adding -0.5 times row 1 onto row 2. All right, so the next step is that we have to divide the second row by -4. So we will now perform that row operation. And now we must add 0.4 times row 2 onto row 1. That will eliminate the entry in the upper triangular quadrant of the matrix on the left. So now we're left with the identity matrix on the left. We applied a sequence of row operations to convert the original matrix into the identity matrix. Each time we applied a row operation, we essentially saved that row, the effect of that row operation in the matrix on the right. Consequently, the inverse of the matrix that we started with is the matrix 0.55, -0.1, 0.125, and negative 0.25. So thus, that is the inverse of that particular matrix. Now, suppose we wanted to find the inverse of this matrix here. Once again, applying the rules of Gaussian elimination and Gaussian elimination to get us to the upper triangular matrix, we add negative 0.3 times row 1 onto row 2. That gives us the matrix there. Now we will multiply row 1 by 0.2. Then we will multiply row 2 by negative 0.5. We will now add 0.7 times row 2 onto row 1. So once again, the inverse of the matrix 5, negative 3.5, 1.5, negative 3.05 is the matrix 0.305, negative 0.35, 0.15, negative 0.5. And if you were to multiply that matrix and the original matrix out in either order, you would always get the identity matrix. Now let us find the inverse of this 3 by 3 matrix. So once again, we set it up with the matrix that we wish to find the inverse of on the left, augmented by the identity matrix. So the first thing we will do is we will swap rows 1 and 2, and then add appropriate multiples of row 1 onto rows 2 and 3 to eliminate those two entries. So doing that in a single step, we have the following. Next, we see that for numerical stability, we will swap rows 2 and 3, and then add an appropriate multiple of row 2 onto row 3 to eliminate that term. All right, so that is what we're left with. This is an upper triangular matrix. It's in row echelon form. It's all the diagonal entries are non-zero, thus the rank is 3, thus the matrix originally was invertible. And now we proceed to continue applying row operations until the left-hand matrix is the identity matrix. So we will multiply row 1 by 0.125, we will multiply row 2 by negative 2, and we will multiply row 3 by 4. This gives us the following matrix. All right, so now we know that this matrix is row equivalent to this matrix here. Well, now the next step is to eliminate everything above the diagonal. So we will subtract row 3 from row 2, and we will add negative 0.375 times row 3 onto row 1. That will eliminate everything in the third column other than the diagonal entry. We now go back and we add negative 1.125 times row 2 onto row 1, and that gives us this rather nice matrix here. The matrix on the left is the identity matrix, and consequently the matrix on the right is therefore the inverse of the original matrix. You can try this out. Multiply those two matrices together in either order, and you will get the identity matrix. Let us now discuss numerical stability. Recall that we saw an example some time ago where if we did not apply partial pivoting, then we'd get the wrong answer from Gaussian elimination. This was because we added a huge multiple of one row onto another. So allowing for partial pivoting, makes it possible for the algorithm to be numerically stable. Now, for invertible matrices, this is essentially equivalent to always putting the largest entry onto the diagonal entry. For if the matrix is invertible, the ultimate matrix in row echelon form will have non-zero entries on the diagonal. Thus, as we're finding the upper triangular matrix, it's likely that at least some of these row operations had to account for partial pivoting. Question: if we have gotten to the point of having a matrix on the left where all the entries on the diagonal are 1, and then we are performing row operations to convert this into the identity matrix, can we ever, under these circumstances, perform a row swap? And you should very quickly realize, no, at this point we cannot perform any more row swaps because that would move a 1 that is on the diagonal off of the diagonal. And so that's not going to help us in reducing the matrix on the left to the identity matrix on the right. So at this point, all we can do is add appropriate multiples of one row onto a previous row in order to eliminate one of the entries above the diagonal of this matrix. So no, we can no longer perform any additional row swaps, and thus if any of the entries above the diagonal at this point were greater than 1 in absolute value, then we may be performing an operation that is going to result in numerical instability. Consequence: finding the inverse of a matrix is not necessarily numerically stable. Now, if you did get to that upper triangular matrix with all 1s on the diagonal, and you notice that all of the entries above the diagonal are less than 1 in absolute value, then actually, yes, finding the inverse will be numerically stable, but you won't know whether or not that's possible just by looking at the original matrix. So we're going to be performing a lot of work to get up to that point. Thus, in some applications of linear algebra to vector calculus, it may actually be reasonable to find the inverse. And in fact, that is what you will be finding the inverse for. Because in those circumstances, finding the inverse will actually be okay. This is because the matrices involved are amenable to this algorithm. However, in general, if you want to solve a matrix A times U1 equaling a target vector U2, and you want to find the vector U1, to get a good approximation, you must apply Gaussian elimination with partial pivoting and backward substitution, and never calculate the inverse of the matrix A and then find U1 by multiplying the vector U2 by the inverse of A. For example, in the third case above, we had gotten to the augmented matrix we see here. In order to proceed to find the inverse, we had to add negative 1.125 times row 2 onto row 1. This was completely unavoidable. We couldn't have done anything else. Consequently, we were adding on the right-hand matrix a multiple of row 2 that was greater, where the scalar was greater than 1 in absolute value. Now, here it obviously didn't cause any serious issues. However, suppose you have a much larger matrix and you're trying to calculate the inverse. You could very quickly get a very large scalar multiple of one row being added onto another. And this may result in numeric instabilities in the calculation of that inverse. To give another example where we inevitably must add a multiple of one row onto another where that scalar is larger than 1 in absolute value, consider this matrix here. Now, if we apply Gaussian elimination and to this matrix with the identity matrix on the augmented side, then we will add negative 0.4 times row 1 onto row 2 and 0.7 times row 1 onto row 3. This results in the following matrix. If we now add negative 0.3 times row 2 onto row 3, we get this matrix here. If we now divide row 1 by 0.5, row 2 by negative 0.25, and divide row 3 by negative 0.2, we end up with this matrix here. Now, thus we have that this matrix is row equivalent to this matrix. So now we will add 3 times row 3 onto row 2 and 4 times row 3 onto row 1. At this point, we conclude by adding 5 times row 2 onto row 1, and thus we have found the inverse. Consequently, the inverse of the matrix in the top left is equal to that matrix on the right. And as you can see, those are actually very, very large numbers, relatively speaking, compared to some of the smaller numbers in that same matrix. Following this topic, you now know an algorithm for finding the inverse of a matrix, assuming it exists. You have seen the application of this algorithm, and you understand that finding this inverse is numerically unstable. Consequently, finding the inverse should be restricted to applications such as vector calculus, where it will be clearer that the inverse is stable. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!